So let's talk real quick. We're going to finish these slides up. There's not much left here, and then we're going to move on into the next chapter, which will be chapter 5. I'm not going to get around to doing NMR right away. We'll just have to see if I can get caught up. So we talked about signal strength. What are factors affecting signal strength? Resonance, polarity, right? The ability to have a dipole, or to have a dipole induced. So if you can have an induced dipole, that also will cause the signal to be large. What about the signal width? We just briefly covered signal width. What causes signal width? What? Hydrogen bonding. Very good. Yeah, OHs, NHs, those are the things that we think of typically that can hydrogen bond. So hydrogen bonding causes peaks to be wide. Anybody remember why? Yeah, it breaks and comes back, right? So when you're hydrogen bonding, when something is hydrogen bonding to the hydrogen, a lone pair comes in, the hydrogen moves away from the atom it's bonded to, and when the hydrogen bond breaks, that is because molecules in solution are moving around, that bond shortens back up again, so that gives you a wide variety of bond lengths and bond strengths. Yeah, so I was going to do something else with this one, but let's go ahead and analyze these spectra and see if we can identify the major components. So, I drew lines. On this side of 3000, we have SP, SP2, and we have O and H, and we have N and H. So those are sort of major things that we'd be looking for. On the top one, you'll notice the signal is relatively small. And down here, this is relatively large. Not as important, but you'll notice that's what this peak to the left of 3000 is coming from these hydrogens. And it's these bonds that we see just to the left of 3000. So if you draw that line at 3000, that's what you expect to see. What is a significant difference in these two spectra? Or these two compounds, sorry. What's that? Oh, no, in the structures, like between this one and this one. It's this carbonyl. And where do you expect to find carbonyls? Yeah, around 1700. Oops. And in particular, if it doesn't have resonance, we find it where? Does anybody remember? Kind of. It doesn't have resonance, just straight like ketone, like acetone. Where do you expect? You guys remember? Well, it's still right at the line I drew, but it's around 17. Do you remember the number? 20. Yeah. 1720. Yeah. Yeah. Just trying to see if anybody remembers, because we went through this stuff pretty fast. Okay, so 1720 is where you expect to find the bond. And if you can see this graph, this is 1500, 1600, 1700 here. So 1720 is actually over here, right? This is the C double bond O stretch that you expect to see. Okay? But it's to the right of 1720. So what do we attribute that to being to the right? What's that? Yes, conjugated, but just if it's moved to the right, what does that mean about the bond? It's weaker. All right, there we go. Because shorter wavelength is to the left, because we do it by wave numbers. So high energy is to the left, low energy is to the right. Okay, so because this peak is moved to the right, even if I didn't have this structure, I would assume that there's some sort of resonance going on. that it's a carbonyl. It's shifted to the right of where I expect it to be. That's why the 1720 is an important number to remember.
So, wait, the right weaker bonds?
Yeah. Because, okay, let's go back.
Shh,
Hang on. Go back to the axis. Go back to the axis. This is 400 down here, which you can't see, and this is 4,000, right? Wave numbers. That's the number of waves per centimeter.
I'm getting the weak, but the weak bonds doesn't necessarily mean stable. Like stable and weak are two.
No, two different things, yeah. You could just think stretchier and not stretchier, right? It's stretchier to the right and not stretchier to the left. I don't know, it's kind of a weird way to think about it, but yeah. Okay, so we see this peak here. Now, you'll notice this is, what's this, do you think? Like, remember we said this is all single bonds in here. So over here, we would expect to see some double bonds. So single bonds are to the right. Those are generally weaker bonds. Double bonds would be sort of in the middle of the spectrum, the middle third of the spectrum. To the left of that, you'd expect to see some triple bonds. In this region that we're looking at here, you're seeing, well, a CO double bond, right? What do you think this is? It's the carbon-carbon double bond. Why would you expect them to be in the same region? Well, they're both double bonds, right? Carbon's not that much larger than oxygen, but oxygen's a little bit smaller. So you expect the oxygen bond to be a little bit further to the left. So once you know where the carbonyl is, because that's a pretty strong CO bond, you expect CC double bonds just to be to the right of those a little bit. So this region, right around here, this is an important thing to remember because it's a landmark. It tells you where a carbonyl should be when they don't have resonance. Sorry, 1720. And then it also helps you remember that all double bonds are in this space. Okay? So I have two double bonds in here. One double bond is the CC double bond, that's this one. And the other one is the CO double bond.
So based on background, C double bond is stronger than C double bond.
C, yeah. And oxygen is a little bit smaller than carbon is. It has a little bit more electronegativity, causes the bond to be a little bit shorter, so it's a little bit stronger. Think through it.
Say it again.
Okay.
CC double bond.
CC, carbon's bigger than oxygen, all right?
No. Yes.
Really? Which is the radius trend goes how?
Oh.
Smallest to the top right, right? So oxygen's a little bit smaller than carbon, so that means the bond strength is going to be a little bit higher just based on that. Plus, oxygen has more nuclear charge. It's
Did you
more
say the carbon-carbon was weaker than the carbon-oxygen bond? Or
Yeah.
stronger?
weaker. Okay. Okay. But if you think about it, there's two things involved in bond strength. One is just how big the atom is, how close together they can get. And the other one is how stable you can make the electrons in the bond. Oxygen has more positive charge in its nucleus. It's a little bit smaller. Its bonds are going to be stronger. Okay, so anyways, once you know where CO is, and we see a lot of COs in this class. We see a lot of CO double bonds, right? Then you'll know where to find CC. So if you see a peak over here, so this is an important skill. If you see a peak over here and you think, oh, I might have a double bonded carbon, right? You automatically have another place to look for verification that you have a double bonded carbon. This is the CH double bond, and this is the CH, sorry, on an sp2 carbon, and this is the CC double bond. Okay. Now, relative height, you notice this is the alkane region, this sp3 carbon region, right? So this is where we expect to find, like these, are sp3 CHs. Okay. That's usually, in most organic compounds of any size, that's usually the biggest peak, simply because even though the bonds aren't very polar, there's just a lot of them, right? Now, it's just kind of interesting. See how big this peak is relative to this? It's about the same size. And here, this peak is a little bit smaller than it is over here, right? What does that imply about the polarity of that bond? Remember, the signal amplitude is related to what? Polarity, right? How polar the bond is. Bigger signals, are there any bigger signals? The bigger signals coming from more polar or less polar? More polar. It actually, the relative size of this carbonyl peak is implying that that bond somehow is more polar. That this double bond, this CC double bond versus this CC double bond, right? Because this CC double bond signal is relatively larger than the signal that's down here, like relative to this sp3, right? It implies that it's probably a little bit more polar. Because its relative amplitude is larger. Oh, I'm doing relative amplitude based on the sp3 carbons.
Based on the highest point.
So based on the amplitude that I'm seeing here and here, that's amplitude is always from the top. Yeah. And then if you do this one, right, the one below, it's this amplitude versus this amplitude. And if you do the relative heights, purple's maybe not the best color for it. Relative heights, this one's actually shorter than this by a substantial amount. This one's actually as big as this one is, except for this real sharp peak that's right here. Okay. Why do you think that bond is so polar? It's because of the resonance. In the resonance hybrid, you put a charge on one end of the double bond, and so it's more reactive to the electromagnetic wave. So the reason I'm just pointing this out is normally CC double bonds, especially if they're internal, are very hard to see. So if you have an internal double bond, what that means is simply it's like that. Okay? They're usually really hard to see because they're nonpolar. If you couple that to something like this, the signals usually get a lot bigger simply because of resonance allows that internal double bond to be polar. So it's something to keep an eye out for if you're thinking about, well, where is this double bond in the structure? If it's really tiny and there's no conjugation involved, no oxygen resonance, anything like that, it's probably internal. If it's on the end, then it's probably it's terminal, right? It's usually bigger than it is than when it's internal. Ran out of air on that one, sorry. Yeah. Okay. We talked about signal width. I'm going to skip over this stuff. So this is the carboxylic acid. The carboxylic acid is very easy to recognize. It has a big C double bond O. It's still around the 1720, 1730 region, right? But then it has this gigantic OH stretch. So remember, OH in an alcohol started around 3600, was about halfway up, and then it stops actually around 3200, which is about here. So you see how it's shifted over. This is an alcohol peak, shifted way over to the right, okay? And that has to do with all the hydrogen bonding that takes place in carboxylic acid solutions. A carboxylic acid, when it hydrogen bonds to another carboxylic acid, right, there's usually two hydrogen bonds going on. And so they talk about these carboxylic acid dimers. That extra hydrogen bonding weakens the bond more, the OH bond more, shifting it further to the right and gives it a lot more width. So this whole peak here is the OH for the carboxylic acid, and this bit that's superimposed on top of it is the CHs from the sp3 carbons. Yeah, it's just buried by all of that. Okay, so typically if you're looking for a carboxylic acid, it's really easy to find because as soon as you look at it, you kind of know. You say, oh, I've got a big peak around 1700. I got a big OH stretch that goes on forever. It's a carboxylic acid. Okay? All right. Go ahead.
So in our lab, when we were analyzing IRs, there was a region that looked kind of similar to this, the OH curve down.
Mm-hmm.
And as you said, the CHs are superimposed on top of that. So it would have been hard to see the CHs. And if there was continuing reactants left over, you'd have, like, we were working with, what was it, acetic acid?
For the banana oil one.
Yeah.
Yeah. So if you actually had some carboxylic acid left in your mixture, like the acetic acid, that would have interfered with your IR spectrum.
Right. So you would have seen PC.
You would have seen a big. This is what an alcohol normally looks like. You would have seen this thing coming out this way. Right. If you had some of the alcohol left, some of the isopentyl alcohol, you would have seen a peak like this one. Okay. And the fact that most of you, in fact, almost none of you had any of that, was a pretty good sign that it was pure. And then, I don't know if you've gone and looked, I posted the GC data so you could put it in your notebooks. Nobody had a significant amount of alcohol in their product. It was all pretty good. Okay. Which is a good thing. Oh, and the eugenol results are up too, and there's 3 people that need to redo it. No, they had their samples, but they didn't prepare them right. So I will talk to you. If I haven't talked to you, I don't think any of you are in this class. So, but there's 3 people that have to remake their samples because you're supposed to add 2/3 full of solvent, and they didn't put the solvent in, so I put it on the GC. I'm here till 11 o'clock at night, and I just start it running, and then I leave, and they didn't have a solvent in it, so they didn't get any peaks. So I have to rerun those, but they'll see when they look at their spectra that they look, or their chromatograms, they look pretty bad. All right. Okay, let's see. For the molecule below, picked all the stretching signals in the diagnostic region. Okay, so the diagnostic region this is going to be 4,000. And what's the end of the diagnostic region? Anybody have a clue? Yeah, 1,500, 1,400, 1,300. I mean, you could read like 4 books and get 4 numbers. Okay, it's around between 1,000 and 1,500 somewhere. Okay, that's the end of it. So let's say 1,400 just for fun. Oh, let's say 1,500 just for more fun because it's easier to split things up. Okay, so there's 1,500. Okay, so let's look at this functional group. That's an alkene. Where would you expect to find that? And just ballpark. You don't have to be exact.
It's double bond, CC,
CC, double bond. So where do you expect to find it? Yeah, just to the right is 17, right? So let's say 15, 16, 17, okay? And it's not linear. I'm stretching it out a little bit, okay? So you expect a peak. You expect a peak about in this region here, right? Because that's my 1,700. You expect a peak here for that CC double bond. How big do you think it'll be? About medium sized, right? Because normally they're medium to weak. This will be a little bit bigger simply because it's got some resonance here. Causes this to be a little bit more polarized, a little bit more delocalized. So you might expect it to be a little bit bigger. So I'm going to say you expect to find a peak here. Why did I draw it sharp? Because it's not going to hydrogen bond or anything like that. You expect one type of bond, right? Okay, now, what else about that particular? Yeah, there's a CH here, right? So now I got to put 3,000 in here. There's 3,000. I'll just call it 3. And I'm going to draw a line like this. And then I expect to find a peak like, and those are usually pretty small. There's not many of them. They're not very polar. Okay? The little peak there. So there's 4,000, 3,000. Anything else? Yeah, so now I have an OH on there, right? What kind of OH is it, though? It's a carboxylic acid OH, right? Now, if I'm being honest, then That's going to be like, oh, let's just do it like this. Oh, sorry, it's not big enough. It's got to be pretty big. It stretches, it starts around 3,600, it stretches over 3,000, right? And then I do have some CH3s in there, right? And I have some, yeah, that's all I have. I really have CH3s. So I expect to see some stuff in here that's just, but it's going to be like a little add-on just because there's only a little bit of CH3 in this molecule. Those are those sp3CH stretches, okay? What else do I expect to see? Yeah, double bonded O, right? And again, that's around 1,700. It is about 1740-ish, 1730-ish. So I will just draw it here. How big is it going to be? Pretty big. Be something like that. And in the diagnostic region, those are probably the main things you would find. Okay? In the fingerprint region, you would find things like CH3 bends. Remember I talked about there's different kinds of vibrational modes, and some of them are stretching, and some of them are bending, like this, they bend. CH3s have a bend around 1370 or something. That's really not that important because it's an alkane, and anyways, it's not as important to identify those things. But the big groups are, you have a C double bond C, you have a C double bond O, you have an OH, right? And then you'll have inside of that OH, because it's carboxylic acid, you'll have some CH3s that are sp3 hybridized bonding, CH bonds. If we are going into the fingerprint region again, you could look for this CO bond is usually around 1100, so you can usually find it around 1100 as well. But that's not really, that's not the diagnostic or functional group range. That's just sort of, if you have it and you want to verify it, you could go into the fingerprint region and look for extra peaks to verify. But honestly, there's so many peaks in the fingerprint region, you can verify just about anything. So, all right. Okay, primary and secondary amines have NH stretching. So primary amine, we haven't gone over this, but a primary amine is a nitrogen with two hydrogens on it. So this is a carbon bonded. A secondary is that. And a tertiary, what do you think tertiary is? All three. So now the question is kind of silly. Why don't you see NH stretches in a tertiary amine? Because there's no hydrogens on it. Yeah, that's pretty much it. Okay, so they can for primaries and secondaries, okay, you expect some hydrogen bonding, right? And so the signals are broader than like CC double bond, for example, broader than that. Now, here's a general question. Which is more polar, OH or NH? OH, right? So what do we usually say about the hydrogen bonding on OH versus NH? You guys remember? What's that? Hydrogen bonding between OH groups and NH groups. OH groups is stronger because the hydrogen bonding effect is bigger because the electronegativity difference is bigger. Okay. So we generally say that OH bonds are more polar, their hydrogen bonding effects are stronger, and generally then OH peaks are stronger. They're bigger because they're more polar. Okay. NH peaks are a little bit smaller, but O versus N in terms of bond strength is about the same, so they end up being in the same region. But their appearance is different because of the other characteristics like the polarity and the weaker hydrogen bonding effects. Okay? So here's an example of a primary amine on the left, and here's an example of a secondary amine. Okay? And what do you notice about the primary amine? It's got 2 peaks on it. It's not as big as you would expect to see for an OH. Right? OH you expect to be much larger. And the peaks aren't as wide. They're a little bit more narrow. A little bit wide at the base, but typically they're not as wide as you'd expect to see in OH. For an NH, that's the secondary amine. You have a single peak, right? And again, it's not as wide or as big as an alcohol. It does still center very close to 3,400. This one's at 3,300, and these ones split around 3,300. Right, now, the reason, I explained this a little bit last time, the reason that the NH primary amines have 2 NH stretches is because they have 2 modes of stretching, and so they could stretch. Remember I did this. That's one mode, and this is the other mode, and each one gives a peak, and they're both in the same area, so that's why you see 2 peaks for it. So that's actually, if you get a primary amine, it's really nice to do the IR spectrum because it's very easy to identify a primary amine. It's got the 2 peaks at the top. Okay. Secondary amine is a little bit harder to tell, but you're not going to call that an alcohol simply because it's too narrow and too short. Right? It's not nearly as broad. Okay, I went over that. So I've done this a couple of different ways, but really when you're analyzing IR spectra, first of all, you usually know your compound, right? So you look at your compound and you identify functional groups, just like we did on that last molecule that we analyzed. And then you focus in the regions where you expect to find different features in the diagnostic range. So for example, you would check for double bonds around 16 to 1850, but if you have a carbonyl, that's a good reference point because the double bonds are usually to the right of the carbonyl, right? So you look for C double bond O's, you look for C double bond C, you look for CN double bonds are also in the same region, okay? Triple bonds will be to that next region over. So if you think about dividing the space up around 1700 to the right around 1700 is where you find double bonds. Between 3,000 and 1,700 in that big middle range, that's usually flat on the spectrum. That's where you expect to find triple bonds. Okay? And then for carbon, hydrogen, for oxygen, hydrogen, nitrogen, hydrogen, this is where you expect to find all those bonds. And then the last thing that you do once you identify them is look at the intensity and shape of each signal to help you verify that's what it is. Okay, so just because you have a peak at 3,300 doesn't mean you have an alcohol. You might have an amine, right? And vice versa. You may not have an amine. You might have an alcohol. But if you look at the shape, that's what tells you it's an alcohol, or whether or not it's an amine, or whether it's a carboxylic acid. Okay. Let's skip over that. I am going to skip these slides. I will let you can look at them. Right. Next. So let's do my homework. It's a very short assignment. Take the time to print out some of the spectra if you can, and then just draw on them and analyze them. It's a much better way to do it, like for people who like to actually do things with their hands. Kinesthetic learners. Okay, so for chapter 5, it doesn't look like a lot of problems, but a lot of these problems have subparts. So for problems with subparts, do 4 unless I say otherwise. So like here, I only wanted you to do 3 of them because it's kind of repetitious. Here I just picked the one I wanted you to do. AC just means do A and C, and all means do them all. As tedious as it might be. Okay. Yeah, and then everything else just do 4. Now, if you need to do 5, if you do 4 and you're like you still don't understand it, right? Send me a text and say I still don't understand it. And I'll probably send back to you, build a model, and then try to do another subpart. Okay. It's fine if you do that. All right, so we're talking about an area, it's called stereochemistry, and stereochemistry has a big effect on the behavior of molecules, physical and chemical properties, okay? We'll skip the can you give some examples. Well, I'll give you a quick example. This is one of those ones from Chem 1A. If I have this molecule versus this molecule, okay, they're going to have very different properties. This molecule on the right, the dipoles essentially cancel out, and this one's nonpolar. And this molecule that's on the left, right, the dipoles actually add together, so this one will be polar. So you expect that to affect both the boiling point and the melting points, solubility, interactions with other molecules, those kinds of things, okay? So 3D structure in biochemistry is very important. So let me give you the how. It's just kind of a more interesting way to do it. So this molecule in the middle is adrenaline, known as epinephrine also. And it's what we designed the drug albuterol from. So what is adrenaline? What is adrenaline? Fight or flight, right? Right? Or it's the Halloween one where everybody likes to jump out and scare people, and then your heart starts to race, you start breathing harder, right? That's all effects of adrenaline. Okay, so one of the things it does, and the reason why it's good for maybe people with asthma, because that's what albuterol is used for, is it's a bronchodilator, and it allows you to get more air into your lungs. When I was a kid, I didn't have asthma, but my brother had horrible asthma, and adrenaline was one of the, you could just get adrenaline, like epinephrine, if you had an asthma attack, okay? And he would have them and be rushed out to the hospital. We were kids, and that was all really scary, but we're all past that now, thankfully. But this is the pharmacophore. That's what this is called. It's the compound that the drug, the pharmaceutical, is designed based off of. Now, one of the things about this drug is that there's an enzyme that eliminates it, and it's called COMT. It's catechol O-methyltransferase. And it turns out in catechol, this is the ortho position. It's called ortho. So this oxygen can be methylated, and that's the first step in its degradation. So the first part in designing a drug is like, how do I keep it from degrading? Right? So you use your pharmacophore. This is the thing you want to be effective. And you modify it. And this was the modification. There's two things to notice on here. One is this OH group. You know how this has got the hatch on it? That means it goes back. This one has a squiggly line on it. That means it could either be in the front or the back. So when they did the synthesis, when they did the synthesis of albuterol, they didn't have a good way of controlling whether it's in the front or the back. Okay? So in other words, even though these things look like they're exactly the same, right? Spatially speaking, right? They have a different shape. I'll give you a good example of that in just a second. But they have a different shape because you can think about it in one. Okay, let's say I'm adrenaline. Okay, so this is my body, and then this is that, right? What does this mean?
It's coming out.
It's going.
Oh, in.
It's going in. So it's like this, right? And then what's coming out of my back?
Phenol?
The hydrogen that's not drawn here, right? Right? And if I'm going to interact with the receptor, this is the shape I have. I find the receptor and I bind to it. Okay? But let's say I make the version of this molecule where this is a wedge. So instead of being like this, now it's like this. My shape is completely different. Okay? And it turns out when I go to find the receptor responsible for the desired effect, I don't fit anymore. Because my shape is different. Okay? So anyways, there's an article some time ago in like the New York Times where they sort of summarized a lot of this stuff. They called it the good twin, evil twin. Oh, so this is one of what's called the metabolites. of this drug. And it's one of the first steps in the process of eliminating it. But you notice what happened here. In albuterol, they added a carbon here. Now, the metabolism of epinephrine is done by an enzyme. Enzymes recognize shapes. So what did they do to keep it from keeping the albuterol from being metabolized? They added an extra carbon in there. Adding the extra carbon in here and not having a methyl group at the end made it so that it doesn't degrade as quickly. Okay. So little things like this, little tweaks of the structure, lead to whole new compounds. Okay. That program that Marvin sketch that I let you borrow is a program that a lot of pharmaceutical companies use. And one of the things that allows you to do is say things like, I want to change this, I want to change that, I want to change that, I want to change what's on here. I have a whole list of things I want to try here, a whole list of things I want to try here, and then it just generates all the structures for you, and then you could have like a map for like how you make all these things from each other. Yeah, and you can imagine, you know, you have 4 or 5 places to attach things. On each position, you have 4 or 5 variations. That's millions of potential compounds. No, I don't think it does do that, but I think, you know, once you have a set of variations, it also calculates like chemical properties and physical properties of compounds. It does all kinds of crazy stuff. We're not talking about that here. But I'll show you how to set it up in the lab if I have time. Okay. Yeah.
Okay, you know how you said that if the OH was wedged like to the back that it wouldn't fit anymore? So
Yeah.
why would you have it the option to go to the front?
Okay, so when they made albuterol, they didn't have the ability to control initially. They didn't have the ability to control which way this thing went. So they ended up with both. So they ended up with a mixture of what we call enantiomers. One's going to the front, one's going to the back, and I'll explain that more in a second. But here's the thing. They did a study, right? This is known as R-albuterol. This is the good albuterol. And this is S-albuterol. This is known as the bad albuterol. What's the difference? Just the wedge. Look at the difference in hospitalization rates.
Wow.
Right? So people come in, asthma attack, right? So they do a study where they finally figured out how to make the 2 enantiomers, the 2 twins, okay? And they could administer them separately or as a mixture. And when they administer them separately, what they found out is that for years they had been wrong in that one enantiomer was harmless and one had the good effect. Turns out one enantiomer had a good effect and one enantiomer actually has a bad effect. But they couldn't separate the 2 before, so they couldn't tell. Okay? So this is the effect of stereochemistry. It's the shape of the molecule is important in its sort of biochemical behavior. Okay, now, all right, I'm not going to do this one. I'm going to make you make some molecules. Okay. I'm going to make one. And you guys make, well, you're going to have to share a little bit. I'm going to take a carbon with 4 holes in it, and each one of you has to make one, and use these medium-sized bonds because we have more of them. You guys not have any at all? We have like, we don't have any. Yeah, you can, from each kit, you can make multiple atoms. I have to be able to make 2.
Yes.
What are we making?
Okay, so this is what I'm doing. I have green, purple, blue, and orange. And I made that. Okay? I want each of you to make one of these. Green, purple, you can use red instead of orange. And we're not concerned about the size of the atom, we're just concerned about the color. Yeah, you can use the bigger one. It doesn't look as pretty in the pictures, but you know, it's whatever. It's good enough. I'm going to change mine so that they're exactly the same. Just less than blue. So I built 2, but you just need to build 1, okay? What's that? No, just build it. Well, it does, but I want it to be random. Hang on. Just waiting for everybody to get caught up. Oh, yours is so pretty. Look at that bright orange.
It doesn't have orange.
I don't have purple though.
That's okay. You have brown. I don't have brown. Okay. So, this is a molecule, okay? This represents a molecule with 4 different groups on it. And what I want you to do is grab it by, let's say, the blue one. Does everybody have a blue atom here? Grab it by the blue one. And then put it, try to match it up with your neighbor. Like, try to see if they match up. No. Got to hold the blue atom. Hold the blue atom. Right? And then go like this. Try to go like this. Try to make a match up.
No. What are they doing?
No, this one will. No, wait. Purple. No. This one, no. Okay, I can't match with you.
Ours match.
Yours matched like this, right? So notice mine. Mine doesn't match, okay? But so I try to make it match. I'm holding purple, and I'm going like this, and it doesn't match, right? You know why it doesn't match? Because if you go like this, watch this. I'm gonna take and do that. I actually have 2 of the same molecule. I did it randomly. I ended up exactly the same molecule. Now, so if yours didn't match, whose didn't match? Anybody's not matched?
We just kept moving it.
Yeah. So all you watch this. I'm going to take 2 of these. Okay. I just switched 2 of them. Okay. And notice what happens. Now they do match. Like that. Right?
Wait, what?
And if you think about like this, see how they're matching? These are actually mirror images of each other. But watch what happens when I do this. I try to make them line up. So I got the green and the blue lined up, but look what happened to my purple and my red. They won't line up. So what does that mean? Like about these two things that I built? They're not exactly the same.
They're mirror images of those.
They're mirror images of each other. But when I try to go like this, I can't. There's no way that I can get those groups to line back up. So these are actually different molecules, and they have shapes. One of these is like the good albuterol with one group in the back, and the other one's like the bad albuterol with the group in the front.
The last test we did.
Yeah, for the Chem 1D.
What's the verbiage for that?
Oh, I'll get into it. I just want you to get the idea. So did you see what I did? Is if I can make mirror images that aren't the same, they are actually like superimposable is what we said. If we can make mirror images that aren't superimposable, then they're actually different molecules. And we call these enantiomers.
No, he's saying something.
Hold it like this. Hold it like this. One blue and one blue. Line the purples up. And yours, right?
Oh, because these 2 are switched anyway.
So now watch what happens. Watch what happens. Take those. Look at this. Watch. See this? Right? So watch what happens when I do this. Yeah, they're the same. So if they're the same molecule, you can't make a mirror image of them.
And if they're mirror image, they kind of
Right.
They're not the same molecule. Yeah. That's the idea. I want you to see it.
Same molecules can be mirror images. They naturally have one switch.
Okay. Hey, back on task, guys. So So this is a kind of, well, okay. We talk about constitutional isomers. What's a constitutional isomer? Same formula, different arrangement of atoms, blah, blah, blah. These are known as stereoisomers. They're actually the same constitution. They're made with the same set of bonds, right? Stereoisomers are made with the same set of bonds, but different spatial orientation of the groups.
We did this at the end of last semester, right? There we go.
Yeah, sorry.
Different orientation of groups?
Yeah, same molecular formula and constitution, but different spatial arrangement of atoms, or groups of atoms on a central atom, okay? So these are known as stereoisomers. Now, this is not the first kind of stereoisomer you've probably seen. The first type of stereoisomer that you've seen was just in the last chapter. And that's when you were doing the Haworth projections. Let me show you on the next slide. Cis and trans, right? What does cis mean? Well, cis means hydrogens are on the same side. Trans means hydrogens are on opposite sides. Now, here's the question you should be thinking about. What do you mean by same side and opposite side? Right? So if you draw a line where this bond is, right, and the hydrogens are on the same same side of that line. So I drew a line through the bond that connects the two atoms, and I draw a line through there, right? If the hydrogens are on the same side, it's cis. If they're on opposite sides of the line, it's trans. Like that. So cis and trans is one kind of stereoisomer. All right. Let's do this. This is our friend butane. He's had some better days. He's lost a couple of hydrogens. This is butane. Why don't I call that trans? And why don't I call that cis? Because it's still the same because it can rotate. Right? In a ring, it can't rotate. And so you can actually make two different molecules. This molecule, cis 1,2-dimethylcyclohexane, is different than trans 1,2-dimethylcyclohexane. Different molecules, different properties. When I do that with butane, because it can rotate, they could be on the same side or opposite sides, but the rotation means it's not a different molecule. So in order for you to have cis-trans isomerism, which is a type of isomer, it has to be constrained.
Better word than
I don't know what you said. But that's the important part. Has to be constrained. Now, if you're looking at other types of molecules, you've seen other types of molecules that are constrained. Here's another type of molecule that's constrained. Hang on. It's a double bond. Double bonds can't rotate. They're constrained. Okay? So you could have a molecule like the one on the left here, right? And draw a line here. And what is that, cis or trans? Cis, because the hydrogens are on the same side. It has to do with where the hydrogens are. Or I could draw a line here. And the hydrogens are on opposite sides, so that one's trans. Okay? Opposite sides of the bond that connects the two atoms. Okay? Or the bonds that connect the two atoms. The constraint is there because of the pi bond overlap. If you rotate it, you have to break the bond. Okay? So you actually get two molecules. You can actually isolate these two molecules from each other. All right, so what we're going to do is see if you guys can pick out some isomers. So this is what you have to do. You have to say whether or not they're constitutional isomers, stereoisomers, or identical. And, you know, on a test it might be neither too, but I didn't do that. So number one, identical. Why? It's a ring flip. You have constraints. You can't rotate it all the way over, but you can do ring flips. And so these two are the same. They can interconvert between each other. There's an equilibrium between those two. So they're the same molecule. What about this one? No. How did you identify? Some people said no already. How do you identify no? So I have two axials on the right, and on the left I have one axial, one equatorial. Right? Can't be the same. Because remember, if they're both axial in one structure and you do a ring flip, they should both be equatorial in the other. Okay? What about the one, number 3? Okay. Draw a line through the double bond.
Oh, wow.
So, and then if it helps you, because we talk about hydrogens when we do this, you put a hydrogen there and a hydrogen there. Which one's that? Trans. And I put a hydrogen here and a hydrogen here. That one's cis. So these are stereoisomers.
So what was number 2? Was number 2 a constitutional isomer or stereoisomer? Stereo, right?
Well, yeah, it'll have to be it is a stereoisomer. Sorry. I was thinking of something else, but yeah, it's a stereoisomer. 4, constitutional. Right, just completely different structures. Constitutional is usually fairly easy in terms of, like, relative to stereoisomers, constitutional all of a sudden becomes really easy because you just say, oh, those are just completely different. If on a test it says constitutional, stereo, identical, or neither, or none of the above, right? You'd have to actually count the atoms in the structures if it was like these two, because you wouldn't know for sure whether or not they had the same number of carbons and hydrogens unless you counted. What about 5? Same. Draw a line like that and draw a line like that. Cis and trans doesn't apply to this, by the way. But if you draw a line like that, you can always see in each structure, there's 2 methyl groups on one side of the line, right, and 1 methyl group on the other. And if you sit down and you really look at this, all you have to do is take the molecule on the right and rotate it. And then you get back to the same molecule. Rotate it in the plane this way. Okay, so now one helpful thing to know about isomers that are cis-trans isomers is you can't have cis-trans isomer if the groups on the ends are the same. So if the groups on this end are the same, like methyl and methyl, you don't have cis-trans isomers because if you flip this bond from this side to this side, you could just rotate the whole molecule over and get back to the original molecule. Okay? So it has to be, in order to have cis-trans isomers, you have to have different groups attached to to each carbon. Okay. Okay. I'm gonna skip that. We already did that. So now we're going to talk about, and this is what we started with because I just thought it's more fun to do. We're going to talk about chiral stereoisomers. Now, a chiral stereoisomer is not identical to its mirror image. Okay? So, in other words, if I, let's see, hold it like this, this molecule is the mirror image of this molecule. Okay? And I try to superimpose them. So what the way you do it's the easiest way to do it is just find 2 groups that are the same. So you're holding groups in your hands and then fold them together like that. And then you'll see these 2 match. Didn't break. Good. These 2 match, but these 2 won't ever match. They're opposite. So these are non-superimposable mirror images. These are chiral. Okay. Your hands, the term chiral comes from handedness. So you have a left hand, right? And you have a right hand. So R, what do you one of the one of the molecules would be known as the R. What do you think R stands for? Right. The other one's S.
Left.
R is actually for rectus or right. S is for sinister. Yes, sinister. Yeah. And that's left-handed. What's Latin? Yeah, of course it's archaic. Because they only speak Latin in Latin America now. Sorry, there's a vice president that said that, I think. There were a lot of good jokes about that time. But, yeah, so R and S. S is left, R is right, okay? So I'm going to teach you how you identify left and right in a little bit. But chiral stereoisomers, we say, are non-superimposable, okay, with their mirror images. Molecules that are superimposable with their mirror images are not chiral. Okay, so chiral means non-superimposable mirror images. If it's superimposable with its mirror image, it's not chiral. So let's show it. This is how you show it with your hands. Take your hands and go like this, right? And go like this. You go Om. No, so you know that. But they're mirror images, right? But you can't superimpose them, non-superimposable, because your thumb is on. Now, if you had two left hands, sorry, then dun. Okay. So we most often see chirality in molecules where an atom has 4 different groups bonded to it. Okay? We most often see chirality, right, when you have an atom in a molecule with 4 groups bonded to it. So, for example, this one in the top, right, I have an ethyl group, a methyl group, a hydrogen, and an OH. Right, those are the 4 different groups. And that's why, you can make the colors match, and you can show that they're mirror images, okay? So let's practice on paper, because it's great having models. You don't get models on the test. We're going to have to see how we identify 4 different groups on a molecule. So on the left, right, this guy over here, what are the highlighted atoms are the chiral centers for each. So for the first molecule, the 2-chlorobutane, right, that's what it's called, what are the 4 groups? Wow. Chlorine, right? Hydrogen, not drawn, so you need to know that. The methyl, and then this whole thing. So you look at everything connected to it, okay? Those are my 4 groups. For the middle one, I'll draw a hydrogen on here like this in the back. So there's one group. There's another group. And then I have ethyl and propyl. Those are different. Now, this one's kind of weird because it's in a ring, right? And there's a hydrogen that goes in the back like this. So bromine and hydrogen, that's 2 of my groups. And then because it's in a ring, you have to look at what it's connected to going in this direction versus what it's connected to going in that direction. If you start at the bromine and you go clockwise, you're going to see carbon that's double bonded to a carbon that's double bonded. And if you go left, you see a carbon that's single bonded to a carbon that's single bonded. At this point here, they're different, so the molecule is actually chiral.
So because there's not symmetrical double bonding.
Yeah, so if I had put a double bond over here and then the molecule was exactly symmetrical going from the left side around or from the right side around, it would have been, we say, achiral. Okay? Would not have had chirality. Part of the trick to that, I think what you just noticed is if it had double bonds on both sides, it would be, I said achiral. Anything that has true symmetry down the middle, right? Left side is the mirror image of its right side, it can't be chiral. Okay. Whoa. Let's not go there. We could test that. Oh, never mind. So one of the other terms that you need to know is something called a stereogenic center, okay, or a stereocenter. These words go together. A stereogenic center just means that if I switch two groups on the stereo center, I'll get a stereoisomer. Yeah.
If you switch
Two groups on the stereo center, I'll get the stereoisomer. So a double bond is actually a type of stereocenter. Okay, it's not a chiral stereocenter, but it's a stereocenter because if I take groups and switch them, I can go from cis to trans, for example. That's not up here. These are just chiral centers. Okay. All right, so let's identify all the stereocenters and chiral centers in these molecules. So let's start with, let's do this. I'm going to start with labeling these A, B, C, and D. I don't know why I didn't go left and right, but it just didn't feel like it's much fun. And I'm going to number 1, 2, 3, 4, 5, and 6. So where are my chiral centers? On A. Where are my chiral centers on A? 2 and 3, right? And then I have a cis-trans type center between 4 and 5. So when you do cis and trans, it actually involves 2 atoms in the stereo center. Chiral centers only involve 1. But that's kind of a nitpicky detail. But. So that's a stereo center. That's a stereo center. And that's a stereo center. My chiral ones are 2 and 3. So what about B? So I'm going to number B. Let me go ahead and number left to right again. 1, 2, 3, 4, 5, and 6. Which ones are my chiral centers? I don't have a cis-trans stereo center, so which are my chiral centers? 2, 3, and 4. Yeah, that's the trick. It's 3 and 4.
Can you knock to the slide?
Yeah.
Definition of chiral. Changing 2 group positions gives a stereoisomer.
Yeah.
That's the definition of a chiral.
Uh-huh. Yeah.
So go back to the other one. I didn't understand why it was not two.
I know. I'll go back to it.
I don't understand. Changing 2 group positions gives.
Yeah. So this, let's say I do this. Right? So here, I took and exchanged 2 groups. I exchanged the Cl and the H. I didn't draw the H, but I exchanged their positions. And this is a stereoisomer of this molecule. Okay, let's do this. Let's actually do this. First of all, make sure the 2 atoms, the molecules you have, are the same. Okay? So that might require you to switch a couple of groups. There's actually a really important principle that's going to come out of this because I'm going to take it a little bit further. But I made mine exactly the same, and I know that because they're superimposable. Okay, I know. Made a giant. That's good. So these 2 are exactly the same, right? So if I try to make them mirror images, I can't. They'll never line up. Okay. Now take one of your molecules and switch any 2 bonds, and keep track of which 2 you're switching. I'm doing green and blue.
On both of them or just one?
On just one of them. On just one of them. Right? And then hold them up to each other. And what do you have? You have mirror images, non-superimposable, right? Because now they don't match. Now here's this. Okay, so I changed green and blue on here, right? Now what I'm going to do is change purple and blue. I'm going to change different ones.
On the same, well, that would take.
Not the same ones. Pick two different ones.
No, I meant the same molecule.
Yeah, so now you end up back with the same molecule. So every time, now there's only a pair of these, right? But you switch two, you get the mirror image. You switch any other two, it doesn't matter. You're back to the same molecule.
Why?
So, all I can say is this is a great time to have a model kit. If I haven't said that already.
It's like the only use that it's useful and like goes
No,
to the closet.
it's useful through the last chapter 4 and chapter 5 are the two most important sections where you actually physically play with models and see what they look like. But this chapter in particular, yeah, it really helps to have models.
So it's just,
What?
the previous slide, it's like you said, so the coin, the first one, coin can go forward or back.
Yeah.
Chapter makes it a,
It can go forward and back, and there's 4 different groups on that center. I have chlorine, hydrogen, methyl, and ethyl. And I took the molecule that I had, I switched 2 of them, and I got the stereoisomer of it. I got the enantiomer of it, is what we call it. Okay. I'll give you that word more. I will add that word to the lexicon in a few minutes. Enantiomer. Enantiomer. I don't know. I'm from Reedley. I don't pronounce anything right. Okay.
I thought there was like going to be a CH.
Hey, Dr. Sher, we're gonna go back to those examples.
Yeah, I was going to go, but I seem to have lost all of my notes on it. Okay, forget it. All right, so we were on B. B was at the bottom. So this was 1, 2, 3, 4, 5, and 6. And everybody, lots of people said 2, 3, and 4 were all stereo centers. And I said, that's a trick. 3 and 4 are stereo centers.
Why?
That's a good question. Why? You answer. What does it have to be a stereo chiral center? 4 different groups, right? Not 4 groups, 4 different groups. So I have a hydrogen back here, right? So I have a hydrogen, I have a methyl. What's that? Methyl. They're the same.
So that's what makes it a stereo?
Yeah, okay, let's do this to ourselves again. Make 2 of your atoms the same on each. I made mine green. This is the necessity of having 4 different groups. Okay, so I'm going to hold mine by the red ones. Oh, I don't have purple on here. That doesn't help. This is the necessity of having 4 different groups. Okay, right? I'm holding it by the green. Yay! Holding it by, oh no, by the orange.
Red.
Sorry. Holding it by the red, orange, whatever that color is. I bring them together. Ooh, they're mirror images. Problem? They're superimposable because these 2 groups are the same. Right? They have to be different for them to be non-superimposable. That's the criteria. That's why 4 is the minimum number of groups that you can have this happen with. We had it in transition metals with 6 and 5 and 4.
How would that work if the, oh, wait, not the US carbon.
Okay.
I got like the 1 carbon and 5 carbons.
All right. All right, let's look at this one up here. What about this one? Does it have chiral centers?
There's 2 the same, so no. Wait a minute. On the left side,
So I have that, and there's a hydrogen that comes like this. And for this one, there's a hydrogen that comes like that. Now, if I start here, I have OH on one side, right? I have an OH, I have an H, I have a carbon with an OH, and I have a carbon with a carbon. It has 4 different groups on it.
Oh.
So that's a stereo center, and that is a stereo center. Okay?
so there are 2 groups that share a common group.
Yeah, they share each other as groups, but yeah. What about D? What's with D?
That one's not because it's the same group on two sides.
D is not, because if you draw the hydrogen down here, that's one group, that's the other group. But the ring going from left, if you're looking at it going up and around and down, or to the right and up and down, it's exactly the same. Okay? And if you think about looking at that from the top, that's what it looks like. Oh, shoots, never mind. That's what that looks like. And you see what I talked about before? It has a plane, it's got symmetric in the middle. It's not a stereo. It doesn't it's not a chiral center. Yeah. Hang on, I don't know how to use this thing quite right. Okay. For B, did you say B?
Yes.
So this is, I had this as 1, 2, 3, and 4. So 3 and 4 are, but 2 isn't. It has a methyl, it has all of this, and it has that, and it has a hydrogen. Yeah, yeah, not just the one bond out. You have to look all the way out, and that makes it chiral. Okay, so now we're going to play this game of draw the missing enantiomer. Okay, so let me back up for a second. Let me give you a word, okay? This is a new word. When an enantiomer, the enantiomer is the mirror image molecule that's non-superimposable. So when you take and switch a bond and it's not superimposable, that's known as its enantiomer. They make an enantiomeric pair. So enantiomers, and there's always a pair of enantiomers. So what we want to do is we want to draw the enantiomer. So what's the simple way to do it? Well, there's different definitions of simple. You can just draw it backwards. So start from, this is the mirror plane, that's the mirror, and then you start here and you go 1, 2, 3, 4. You notice how what I just drew is the mirror image? And then the mirror image would have this. So that's an enantiomer. How else could I do it?
Because if you flipped it, then the chlorine would start coming out.
Yeah. The other way I could do it, I could switch the Cl and the H. So I could do the mirror plane trick, that's this, just drawing the mirror image of it. Or I could just do it like this. I could draw exactly the same molecule. And then instead of having the Cl in the front, have the Cl in the back. Like that. And that would also be the enantiomer. No, chiral means non-superimposable mirror image. Enantiomer, right, it refers to the two, like your enantiomeric. That means it's talking about the molecules. Chiral simply means it has a non-superimposable mirror image. It's the kind of the process of, I don't know how to, I'm not English, so sorry. Remember I told you I blew those classes off.
I thought you guys took the 5-piece carbons out of the index.
Some of them we did.
Yeah, keep on getting messed up by 5-piece carbons.
Okay, so this is what we're going to do, just for fun. I'm going to keep my purple and my orange, because I like purple and I like orange. And I'm actually going to build that molecule without putting the hydrogens on it. I just want to show you this. you may or may not be able to keep up with me on this one. Okay, so I take this molecule. That one's exactly the same, right? And all I'm going to do is I'm going to take this and switch them. So like I did at the top. So if I do that and pull that off, and I pull that off, and I put it in like this. So now I have that, right? And I just flip it around like that. And you notice how the orange is in the front? So what I did was took this molecule, the Cl and the H, and I switched them, and that's actually that molecule there. Okay. The other way to look at it is I just made that one. But this and this are the same. They're just rotations of the same molecule. Okay? So some of this you just have to, like, it's early in your stereochemistry career. If you can't visualize it, you just have to be very organized. Take it on faith that if it's got a chiral center and you switch two groups, you just made the enantiomer. Because these are the smallest molecules that we'll see, and they get much larger after this, okay? So you have to recognize, hey, I switched two groups. That's the enantiomer. And go, huzzah, this is good.
If you have the enantiomer, you switch two groups,
Yeah, so if I took that, right, this is, you can see how these are mirror images of each other. If I take this, and I switched to purple and red before, now I'm going to switch the groups like that. I switched the black groups, right? I'm back to the same molecule. Yeah, I know, but hey, you know what? If you get a model kit and you build them, it's a lot easier. Will I say that to you repeatedly until you get a model kit? Probably, and hopefully it's not too late then.
So we can use it on the test, though, right?
No, not allowed on test. Okay, so we're going to talk a little bit about nomenclature. I'm just going to set you guys up. We'll do nomenclature next time. But these two molecules look exactly the same. But what is their relationship? They are
Those are enantiomers.
enantiomers. Okay, so an enantiomeric pair. If you were to name it, this is known as a alkyl halide, because it's an alkyl group with a halogen on it. The name for that would just be 2-chlorobutane. Well, that doesn't sound right, does it? So both of these are called 2-chlorobutane. That can't be right because in nomenclature you have to have a way to distinguish one from the other. So what we're going to be doing is learning out how to distinguish the R. Remember we talked about R and S? We're going to learn how to distinguish the R from the S. Okay? We'll do that on Tuesday.